see this slide?
Yes, sir.
Okay. Bismillahirrahmanirrahim. So I will start structure mechanics and structure mechanics part 2 with you guys. I will be teaching plane stress transformation and plane strain transformation. In case of plane stress transformation, we will be studying about the analysis of the stress. So basically, how we will proceed, that first we will proceed from three-dimensional element. From the three-dimensional element, we will proceed towards the two-dimensional element. And in the two-dimensional element, we will first find out the stresses, normal stresses, shear stresses over the element. And then from there, we will proceed towards the computation of the transformed normal and shear stresses, principal stresses, uh, this principal, what you say, maximum in plane shear stresses, orientation of the principal plane, shear planes. Fine. So actually, in the first half of the chapter, transformation of stresses, we will be deriving equations, ठीक है जी, for the computation of the stresses, ठीक है जी, acting on the element. Then in the second half of the chapter, we will work on Mohr circle. Mohr circle is a graphical solution. It will give us the same what you say, you can say the information or the quantities which we can get from the equations. But Mohr circle is more simpler solution in the sense that from one circle you can get all the values. You can get your normal stresses, shear stresses, you can get your principal stresses, maximum incline shear stresses, orientation of the principal planes, orientation of the shear planes. So everything you can get it from the Mohr circle. Mohr circle is like a graphical solution. Then after the mids, we will repeat all this with transformation of the strain. So transformation of the strain will also be similar. In the transformation of the strain, we will, what you say, study this derivation of the equations for the computation of this, what you say, normal strain and shear strain, then the computation of the principal strains, maximum in plane shear strain, and so on. Fine. Again, in case of the transformation of the strains, we will work on the Mohr circle, and that will be Mohr circle for plane strain. And from the Mohr circle, we will again get transformed normal and shear strains. We will get the principal strains, maximum in plane shear strains. We will get, what you say, orientation of the principal planes, orientation of the shear planes. Okay? So Mohr circle is a graphical solution. So in both chapters, in the first half, we will study, we will derive the equations to compute the stresses. Okay? And then in the second half, we will study the Mohr circle. And in the Mohr circle, we will it's a graphical solution which will give us the same quantities which we had found earlier using the equations. In the strain transformation chapter, we will also derive the equations which will develop the relationship between stresses and the strains. Find using different elastic constants like modulus of elasticity, like the Poisson's ratio. Fine. And in the last weeks, we will study this experiment stress analysis. This experimental stress analysis by strain-Rosette solution is actually similar to the strain transformation. So what we do in this strain-Rosette solution, we will attach the strain gauges on the beam element. Okay? Let's say you have a beam element and you attach the strain gauges on the beam element. ठीक है जी, let's say one strain is truly perpendicular, other strain is 45 degrees to the perpendicular strain gauge, and the third strain gauge is horizontal. ठीक है जी, so this pattern of strain gauges, this can vary. So this one particular pattern of strain gauge, it will give, it's basically a strain rosette, and strain rosette solution is that you will practically measure the strains from the strain rosettes, and then using these elastic constants you can calculate the stresses, normal stresses, shear stresses, and so on. Then the last thing that we will cover in this subject with me, you guys will cover with me, that is theories of failure. ठीक है जी, theories of failure for ductile materials and brittle materials. As you have seen that we have studied in the tension test in our lab that mild steel specimen, it will fail in a ductile manner in forming a cup and cone, whereas your cast iron specimen in tension, it will fail under what you say, it will exhibit brittle failure. ठीक है जी, now it will have like very smooth surfaces and it will fail brittly. Similarly, in torsion, your mild steel specimen, it will fail like in a very smooth manner, whereas your cast iron specimen will fail at 45 degrees in torsion. Now, to explain these four different types of the failures, ठीक है जी, to explain these four different types of the failures, one for the ductile, other for the brittle material tested in tension, and the third for the ductile, and fourth for the brittle material tested under torsion. So you will have four different types of the failures. Now those four failures will be defined or will be justified with these four theories. So we will study four theories. Two theories are related to the ductile material. There are two theories are related to the brittle material. ठीक है जी? So this is a brief what you say description of the different course components which we will study, and we will study them in quite detail. Total we have 8 weeks for this transformation of stress and transformation of strain chapter. ठीक है जी, and we will split these chapters in two halves. In before the week 5 to week 8, we will have transformation of stresses chapter. Then in the after the mid, from week 13 towards week 16, 13, 14, 15, and 16, we will study the transformation of the strain. One more thing I would like to share with you guys, that structure mechanics, it is like mathematical subjects. It's all mathematics. You will just derive the equations and you will solve the numericals. Theoretical part is very less. ठीक है जी, you will just be studying few theories, but even in those four theories, you have a lot of derivations to do. ठीक है जी, because you have to draw the failure planes, and to draw the failure planes, you need to find the failure points, or you can say you have to derive those failure points. So structure mechanics, it's very mathematical subject, and if you will work hard, you can really score very well in this subject. This is the course contents. These are the course contents which you will cover with Dr. Numan. ठीक है जी, I think you guys have already studied this by axial bending, and this shear stress distribution, I think you guys might have started. But these are all the course contents that you will study with Dr. Numan. ठीक है जी, so these are the course contents which ठीक है जी, so these stress transformation, these stress transformation, strain transformation I will cover. And the book which I will follow is R.C. Hibbeler, 8th edition. R.C. Hibbeler, 8th edition, stress transformation, what you say, chapter number 9 is stress transformation chapter, and chapter number 10 is strain transformation chapter. Okay, so we will be following R.C. Hibbeler 8th edition. As you know that we are studying in outcome-based education, the OBE system. Now, in outcome-based education, there are program educational objectives (PEOs). Then there are your civil engineering degree has 4 program educational objectives. Then those 4 program educational objectives are mapped with 12 program learning outcomes, PLOs. You have 12 PLOs. Then those 12 PLOs are linked with or mapped with number of CLOs in each subject. So similarly here in structure mechanics, you have 5 CLOs, course learning outcomes. So first CLO is to compute the principal stresses and principal strains when the member is subjected to complex loading. This CLO is mapped with PLO4. PLO4 is your PLO about investigation. PLO4 is investigation. And the Bloom's taxonomy for this CLO is C3. C represents cognitive. Basically, it means it's knowledge. Uh, 3 stands for the mild difficulty level. C1, C2, these are low difficulty level. Or mild difficulty level. 3 and 4 we can say is medium difficulty level. 5 and 6 is high difficulty level. In analysis subjects you will mostly see C3, C4, C3, C4 because these are analysis subjects and they are considered as medium difficulty level. In the design subjects you have mostly Bloom's taxonomy level C5, C6 because design is considered as higher, has more difficulty compared to the analysis part. So the second CLO that we will study is to compute the bending stresses in the section subjected to unsymmetrical bending. This CLO is linked with PLO4, and Bloom's taxonomy is C3, cognitive mild difficulty level. Then the third CLO is to calculate the stresses and the strains in shells applying thin and thick shell theory. So Bloom's taxonomy for this is C3 and PLO is 4. To calculate the stresses and the strains in shells applying thin and thick shell theory. So it is Bloom's taxonomy is C3 cognitive mild level of difficulty. Then you have fourth CLO, that is to analyze the columns subjected to various loads and different end conditions. So this is linked to Bloom taxonomy C4, cognitive 4, and it is linked with PLO2. PLO2 is analysis. PLO1 is engineering knowledge, PLO2 is analysis, PLO3 is design or solution. And the PLO4 is basically your investigation. In most of your subjects, you will see you have PLO1, 2, 3, or 4. Now over here in this structure mechanics, there is another CLO, CLO5, that is to exhibit commitment towards time management, punctuality, and honesty. Bloom taxonomy for this is A3, affective domain, and mild difficulty level. PLO is ethics. ठीक है जी. So this CLO we will evaluate based on your class participation, on your timing, that at what time you are entering into the class. If you are coming late, then you are not regular. ठीक है जी. We will also give you some assignments. ठीक है. And you will do those assignments within the prescribed time, and you will return those assignments. Then these are the CLOs related to the lab part. I think we have covered, or you can say discussed these CLOs in our lab. ठीक है जी. If we have not discussed, we can discuss it in the lab. ठीक है. Now the books. So for my what you say course, plane stress transformation and plane strain transformation, it is R.C. Hibbeler, Mechanics of Materials, 8th edition. I have this book in soft as well. Just if you can give me a moment, I can share the link of this book. I have this book placed on the OneDrive, so I can share the link with you in this in your team, and you can download that book. Just give me a moment. Structural mechanics. Just a moment, I'm just sharing the link of the book so that you can download the book. Book is bit. Guys, did you receive the link? So this is the link to the book. I cannot email the book because it's 77 MB. So I have uploaded it on OneDrive and I'm sharing the link with you. So you can download the book. And I will be following this book, R.C. Hibbeler, Mechanics of the Materials, 8th edition, published by Prentice Hall, 2011. One more thing is we are going to follow chapter number 9 and chapter number 10 of this book. The other books which you can use basically for Dr. Numan's portion, they are Andrew Pytel and John Quaslas. Then you can use this Ferdinand book. Zahid Ahmed Siddiqui book will not cover much here. So these books you can use. For my portion, I will be following this R.C. Hibbeler, Mechanics of Materials by Mechanics of Materials, 8th edition. Okay, so now let's start with what you say, the introduction of the subject. Introduction of the subject, structure mechanics. So structure mechanics or mechanics of the structures is computation of deformations and deflections and stresses or internal forces. Stress is force per unit area, so that's why they are saying internal forces. So structure mechanics is the computation of deformations, deflections, internal forces, stresses within the structures. Either for the design or for the performance evaluation of the existing structures. Means to say, if you recall in, guys, please keep your mics mute. So means to say that for the design of the structure, you need the loads. ठीक है जी, you need the load. If you recall, in your steel structures you have designed the elements, ठीक है जी, you have designed compression and you have designed the what you say this flexure members. So in the design, uh, before the design, you had some values of the loads like dead loads, live loads, and then you have the span lengths. Then on the basis of this, you designed it. Now here, basically, we need to calculate those critical loads or stresses. That's Mohammed Hansla Tahir, please keep your mic mute. So here we have to calculate those stresses and the forces so that those stresses and forces can be used for the design of the structure. Okay, so in this mechanics of structures, basically it's analysis. So in analysis is we compute the deformations, deflections, we compute the internal forces, stresses, okay, and then based on those deformations and the stresses, you will design the structure. Other thing is performance evaluation. This is for new structure design. Okay, we are calculating the loads for the design of new structure. The second thing is calculations of the loads for the performance evaluation of existing structure. You might have seen structures general design life is, let's say, 25 years, but even after 25 years, your structure is performing reasonably. So you want to see that how much is the strength, ठीक है जी, capacity of the existing structure. So for the existing structure, what we do, we take the cores out of the slab, beams, columns, walls, ठीक है, just like the cylinders, ठीक है. In your PRC lab, you will cast the cylinders to get the compressive strength, ठीक है, for the new concrete. But for the existing structures, for the existing structures, you can get the cores from the beams, columns, slabs, walls, and then you test those. Then you can test what you say those cores under the compression. When you will test under the compression, you will get the compressive strength. Then you can know that okay, the structure was designed for this loads, and now it has this capacity. So you can have an idea. Okay, structure has 80% capacity, or now the structure has 70% capacity or 90% capacity, depending on the conditions. Because see, due to what you say, corrosion, due to carbonation, and due to acid attacks, your concrete strength reduces over the time. So we want to evaluate the existing structures as well. So in the structure mechanics or mechanical structure, you will calculate the deformations and the stresses within the structures, both for the new design of the structure and for the existing, you can say, performance evaluation of existing structures. Structure mechanics. Structure mechanics. Now for the computation of these loads, the final loads or the stresses or the deformations, you need to give some input data. Input data is that how much superimposed dead load is acting over the structure, how much wind load will be acting over the structure, uh, whether we have to design the structure for earthquake loading or not. Because nowadays even Pakistan Building Code has the requirement that structure must be designed for the earthquake. So you have different scenarios, or you can say you have different levels, level 1, level 2, level 3, level 4. So accordingly you will design for the earthquake. So we have to consider wind loads, uh, dead loads, live loads, earthquake loads, then we have to consider the structure geometric representation. In general, you have seen geometry of the structure is rectangular or square. Uh, the reason for this geometry, structural or rectangular, is because of the what you say formwork. It is easy to have a formwork of rectangular shape. However, in the rectangular or this what is the square shape, you have stress concentrations at the edges. So your these edges are basically relatively weaker part. Whereas in case of other geometric representation, the most important and second most common representation is the circular geometry. Circular geometry is best. The reason is that in circular geometry there is uniform stress distribution. There is no point which is under stress concentration. The structure has uniform stress distribution. However, circular cross section is relatively difficult to construct because of the formwork. So that's why you see more rectangular geometric being particularly columns and lesser what you say circular columns. The reason is the formwork, the labor cost. However, the geometry which is best will be circular because it will help you to have uniform stress concentration. Then support conditions. In case of the columns, you have pin-ended columns or hinged columns, or you have this fixed-ended columns, or you have one end fixed, other end free columns. Then in case of the beams, you have fixed-ended beams, you have simply supported beams, then you have one end fixed, other end free. So all these are basically support conditions are required for the analysis of the structure. You have seen this in your elementary structure analysis and structure analysis. Like in elementary structure analysis, you were analyzing the determinate structures, whereas in structure analysis, you were analyzing the indeterminate structures. You were calculating fixed end moments directly from the formulas into force method. Then in your elementary structure analysis, you were analyzing determinate and simpler structures, and you were using Castigliano's theorem to calculate the deformations as well. Then comes the material properties, because we will be dealing with concrete and steel mostly. So in case of steel and concrete, the main materials which can be used, material properties which are required, they are modulus of elasticity. That is modulus of elasticity and Poisson's ratio. Modulus of elasticity is basically over slope of the elastic axial stress strain curve. Within the elastic portion where the Hooke's law is applicable and stress is directly proportional to the strain. And Poisson's ratio is basically a ratio of lateral strains to the axial strain. In case of the steel, Poisson's ratio is 0.3, whereas in case of the concrete, Poisson's ratio varies from 0.15 to 0.20. So different materials have different modulus of elasticity, different Poisson's ratio. Modulus of elasticity of the steel is 200,000 megapascals or 200 gigapascals, whereas the modulus of elasticity of the concrete, it is a function of the concrete compressive strength. So generally you can have for normal strength concrete modulus of elasticity varying from 28,000 megapascals to 30,000 megapascals. So in the structure mechanics, you will analyze the structures giving the input data structural loads, the different types of the loads acting on the structure, geometric representation, support conditions, and the material properties. Okay, and the output quantities which you will get. Output quantities which you will get, that will include the support reactions. Okay, then stresses. Here you will have two types of the stresses: normal stresses and shear stresses, and displacements, deformations and deflections. ठीक है जी? So output quantities may include support reactions, normal and shear stresses, displacements and deflections. Any questions? Okay. Now there are three different approaches to the analysis. Okay, we have three different approaches to the analysis. One is energy methods, second is finite element method, third is plastic method. Just like your design in steel structures, you said there are three design approaches. One was allowable strength design, second was load resistance factor design, third was your plastic analysis and design. Okay, now similarly here you have three approaches. The first approach, and which is the most common approach, energy methods. Okay, you have studied Castigliano methods, you have studied moment area methods, so they are all energy methods. So energy methods, they expresses the relationships between stresses, strains, or deformations, displacements, in terms of material properties. Now, when I say strain, when I say stress, stress is force per unit area. So basically, with when you will, let's say if you have a beam and you apply the load. So with increasing applied load, the cross-sectional area is constant. Okay, so with increasing applied load, what will happen? Your stresses, axial stresses will increases. Okay, the axial stresses will increase. So stress is force per unit area. So with increasing force, your stresses will increase. Then you have the strains. Strain is change in deformation over the deformation over the original length. So strain is basically a ratio. Okay, जी? Ratio of deformation, change in deformation to the original length of the material. Material properties, modulus of elasticity, Poisson's ratio, these are the two main material properties. So we will develop over here as well, we will develop the relationships, okay? Like as we were saying in strain-Rosser solution, that if we calculate the strains, we can get the values of the stresses. How you will get the values of stresses? Because you will be using the relationships, okay, which link the strains with the help of the material, okay, the modulus of elasticity. So with the help of the modulus of elasticity, you will get the stresses. Okay, the stresses is equal to modulus times strain. Okay, the same Hooke's law equation. So over here it will be more elaborated because we will have stresses in x, y, and z dimensions. So similarly, we will measure the strains in different dimensions, and then we will calculate the stresses using the relationships between stresses and strains. External effects in the form of the energy or work by the internal forces. You guys have also studied the virtual work method, which gives you the external work done should be equal to the internal work done. So all the methods which you have studied so far, most of them are energy methods, in which you have the relationships between the stresses, strains, deformations, displacements with the material properties, modulus and Poisson's ratio. your displacement method, your force method, which you will study in higher classes. They are all energy methods. Okay. Then comes the finite element method. Finite element method is mostly, you can say, a numerical method. ठीक है जी? Numerical method. Numerical method means that you will use the softwares. ठीक है जी? Just like we can take the example of ANSYS. ठीक है? So how this finite element method? Finite, basically this word finite means that I will have a beam element. Let's say I take a beam element. I will divide it into smaller number of units. Okay? So finite number of units. I will divide the structural element in finite number of units. Okay? So after I have smaller number of units in computer system, each unit is analyzed. Then the results, the softwares will converge the results of all the units to give you one value of stress and deformation. Okay, how the computer system ANSYS or Abacus will work? You will have an element that number of you can say finite number of smaller units. Each unit will be analyzed. Each unit will be analyzed, and then the software will converge the results of all the units to give you one value of the stress and the strain. To give you one value of the stress and the strain. When you will be doing this manual calculation, when you will be solving the units manually, you don't solve all the units. You just take the one unit which is the true representative of the element, and then you solve that one unit. We get it theoretically to get the stresses and the strains. So here we will be doing this, that we will split our element into smaller number of units. Then we will analyze one unit. We will calculate the normal stresses, shear stresses, normal strains, shear strains, principal stresses, principal strains, maximum in-plane shear stress and shear strain, orientation of the principal planes, orientation of the shear planes for one unit. Okay, and we can like have the opportunity that if we can calculate the strains, we can get the stresses, or if we have the stresses, we can get the strains as well, because we have these physical properties like density, Young's modulus of elasticity, shear modulus, Poisson's ratio, coefficient of thermal expansion, thickness. These physical properties can be used to develop the relationships between stresses and the strains. And you can do the analysis, you can calculate the stresses or the strains, and then using these relationships, you can calculate the unknown. Okay, so your computer softwares, they are working on finite element method. Even you can develop the Excel sheets for the analysis. Fine. So in that analysis, you can split your element into finite number of layers, and then you can analyze each and every layer by just writing simple programming. Simple loop commands, you can write it and it will analyze each layer for you, and then it will consolidate the stress results to give you one value of the stress and the strain. Next is plastic analysis approach. Now, if I will, before going there, I would like to share one. One second, guys. I would like to share this figure with you, which we have drawn in, I think so, lab class. It needs to be discussed here again. Now see this. Now see this. This is the stress strain curve. You get it? Now you see this. This is linear elastic stress strain portion of the steel, then yielding, strain hardening, and necking zone. Now when we do the design, we are assuming the stress strain behavior of the steel as biaxial stress strain. Linear elastic followed by the yielding. So biaxial stress strain curve. Now the thing is, when you assume this by axial stress strain, you are not considering this ultimate stresses, you are not considering the strain hardening or the necking zone. ठीक है जी, आप ये वाली zone नहीं consider कर रहे हैं. Fine. Now in the plastic analysis, what we are doing, instead of taking bilinear stress strain of the steel, we are considering this strain hardening and the necking zone. We are considering the inelastic range. We are considering the ultimate strength. So this is basic difference between plastic analysis and the other approaches. In the other approaches, you are just going after the yielding, but in the plastic analysis and design, you are going in the formation of the plastic hinges. Means the you are going more towards the failure. Okay? So plastic analysis approach. Plastic analysis approach is what you say more advanced as compared to the other approaches, because now you are considering the inelastic ranges instead of just elastic limits. So what will happen in your design? You will utilize the full strength of the material. So what will happen? Your size of your element, structural element, the size of the structural element will reduce. Okay? Your structure will become more slim. Okay? And good designer is the one who basically design like economical design, more slim structures rather than designing more bigger structures, because design is economy. So you can make your structures economic if you use this plastic analysis approach. So here we will also discuss the analysis, plastic analysis. So plastic analysis is defined as the analysis in which criteria for the design of the structures is the ultimate load and not the yield load, and it is the analysis in which inelastic material is studied beyond the elastic limit. ठीक है जी, inelastic material is studied beyond the elastic limit. ठीक है जी. Plastic analysis, the two commonly used methods are, one is equilibrium method we use, other is this virtual work method we use, and we do it in very much detail in MSc, where we analyze beams, where we analyze the frames. ठीक है जी. So here I want to have to give you some idea about the different approaches available for the analysis: energy methods, finite element method, and the plastic analysis approach. Guys, we will have a guys, we will have a break now. So if you have any questions, prayer break as well. So if you have any questions, please ask me now before we have a break. No questions? Let's continue with our introduction of the structure mechanics. So now we are going towards more specific introduction, that is about the stress transformation, or you can say plane stress transformation. Normal forces, shear forces, bending moments, and torque. So these are the few things which we need to discuss. Because in this structure mechanics, when we will be analyzing the element, we will be computing normal stresses and shear stresses. So first we need to understand that how normal stress and shear stress is produced in the element. So normal force, as we know that the stress is equal to force over unit, force over area. Area is your cross sectional area, remains same. So with changing value of the force, there will be changing stresses. So normal force is the force which acts perpendicular to the area. So normal force acts perpendicular to the area, and it is developed whenever the external loads tend to push or pull on the two segments of the body. Now, push is that if your force tries to compress the element, tries to shorten the element, ठीक है जी, that is the push force, tries to shorten the element, that will be your compressive normal force. On the other hand, if your normal force tries to extend, tries to elongate the element, ठीक है जी, trying to pull the element, that will be your tensile normal force. ठीक है जी. So tensile normal force is considered as positive and it will produce tensile normal stresses. Compressive normal force is considered as negative and compressive normal force will produce compressive normal stresses. ठीक है जी. So normal forces is the force which acts perpendicular to the area, and the normal force is developed whenever the external loads they tend to push or pull on the two segments of the body. So due to the normal forces, there will be normal stresses. Positive normal stress is your tensile normal stress, and negative normal stress is your compressive normal stress. ठीक है जी. Then comes the shear force. Then comes the shear force. Shear force lies in the plane of the area, as we have discussed earlier as well, that shear force, it lies in the plane of the area, and it is developed when the external loads tend to cause the two segments of the body to slide over one another. So shear force is the force which tries to cut the element into two halves, and the shear force will produce shear stresses. Shear force will produce the shear stresses. So two things you need to remember: normal stress and the shear stress. Normal stress will produce tensile stress or compressive stress. Shear stress we will be using just one value of the shear stress. Okay, that is the positive shear stress. Okay. Then comes the bending moment. Okay, bending moment and torque. Bending moment is caused by the external loads that tend to bend the body about an axis lying within the plane of area. So what the bending moment will do, it will bend your element within the plane of area. Now this bending moment can be positive or the bending moment can be negative. Sagging is your positive bending moment when the tension is at the bottom and compression is at the top. Then you have negative bending moment, that is hogging. In hogging, tension is at the top and compression is at the bottom. So bending moment is caused by the external loads that tend to bend the body about an axis lying within the plane of area. Then you have torsional moment or torque. Torsional movement or torque. Now, the torque we have defined earlier, that if you have an element and one end is what you say, one end is fixed, and on the other end you apply the force. ठीक है जी? external loads, which tries to twist one end of the body with respect to the other end of the body, okay, in an axis perpendicular to the area. In case of the bending, whole of the member will bend, whereas in case of the torque, one end is like fixed, other is moving. So there is like twist is produced in the element. ठीक है जी? So normal forces, these are the forces which act perpendicular to the area. These will produce tensile forces and compressive forces. Shear force is the force which lies in the plane of area. It will which tries to cut the element into two halves. Shear force will produce shear stresses. Bending moment is the bending of the element within the plane of area. They can be hogging, they can be sagging. Torque or the torsional moment is produced when external loads twist one end of the body with respect to the other. And in the torque, there is no bending. It is twist. Okay. Shear stresses, because we will be concerned about these normal stresses and the shear stresses. So what are the normal stresses? The stresses which are produced by the normal forces. Normal stress is intensity of the force acting to applied area, ठीक है जी, is defined as the normal stress. Okay? If the normal if the normal force or stress applies the pull on the applied area, it is referred to as the tensile stress. Whereas if the normal force or the stress pushes on the applied area, it is referred to as the compressive stress. Is this clear? So normal stresses, they can be either tensile or compressive. Tensile normal stresses, they are basically produced by the tensile normal forces. Compressive normal stresses, they are produced by the compressive normal forces. Tensile normal force is considered positive. So similarly, you can say this tensile normal stress will be considered positive, compressive normal stress will be considered negative. ठीक है जी? This is sigma, and this is the sign which is used to represent normal stress. ठीक है जी? Then the second thing is shear stress. Shear stress. So intensity of the force. Shear stress is intensity of the force acting tangent to the applied area. Is called as the shear stress. ठीक है जी? So shear forces which are acting in the plane of the area, which are trying to slide one segment of the element over the other, these shear forces, they will produce the shear stress in the element. So we will be now talking about these what you say, normal stresses and the shear stresses, and when we will analyze over the element there will be normal stresses and the shear stresses. Okay guys, so this stress, normal stress and the shear stress is clear. Shear stress is represented by torque. Is this clear? Okay, next is the reference planes. Now, if you look at this figure, over this body, these are the external loads, P2, P1, P3, P4. Okay, this is your external, this is your body, and these are your external loads acting over the structure. ठीक है जी. This O is any you can say a reference point which is selected. So if we cut the what you say body into two halves, ठीक है जी, along this plane AA and then along this plane BB. So if I cut the body into two halves along the plane AA, I get this figure. And you can see in this section P1 and P2, these are the two external forces acting. This is the O, this is the plane above which you have cut the element. Now you can see this, you can calculate the resultant normal stress and the resultant shear stress acting on the element. Then we have cut the element along the plane BB. We have cut the element along the plane BB. So over the element, these are the external forces P1, P2. This is the center O, and these are the resultant normal and shear stresses. Now, the important point to be noted here that when you will cut the element along two different planes, okay, along two different reference planes, the normal and the shear stresses, the normal and the shear stresses in these two cases will be different. So stresses acting at a point or in a body depends on the orientation of the reference plane. Okay, so this is one reference plane AA, this is second reference plane BB. So stresses acting at a point in a body depend on the orientation of the reference plane. The two sets of the stresses, set means normal and the shear stress. The two sets of normal and the shear stresses would not be equal. Okay, I am highlighting this so that you remember this. Okay, would not be equal, although they are computed at the same point. You can see your plane AA and plane BB, they are passing through the point O. The two sets of the stresses would not be equal, although they are computed at the same point, because the resultant forces acting on the two planes AA and BB, they are not equal. The resultant forces you can calculate, you can see the area. Okay, the area in the two cases is different. So the resultant forces acting on the two planes will not be equal. Is this point clear? Is this point, guys, clear?
Yes, sir.
Yes, sir.
So your normal stress and your shear stress will depend on the reference planes. They will depend on the reference planes. Okay, next, now in the continuation of this, we want to calculate the stress at arbitrary planes. So this was the example which we were talking about at the start, that this is my element and I divide or separate this element into finite number of units. So this is one unit. In the computer aided analysis, all the units will be analyzed, and then the results will be converged to get one cumulative value of the normal and the shear stress. However, in case of theoretical calculations or manual calculations, you can see I am considering just one unit. Okay, so this is one unit, and you can see on, sorry. So you can see on this one unit, these are the normal stresses, normal stresses, and this is the shear stress. Then this is represented on two-dimensional. Take a top view of the element. You can see now the shear stress and the normal stress. So now all the formulas which we have studied earlier, because they are applicable to specific planes. Okay, it's not that you can apply these stresses to any plane. Okay, so it is usually not practical to directly compute the stresses acting on arbitrarily chosen planes, because the available formulas give stresses on certain reference planes only. It gives stresses on certain reference planes only. For example, Fletcher formula is restricted to the normal stress on the cross-sectional plane of the beam. EKG. So Fletcher formula, which we have studied, or which you guys have studied in mechanics of materials, and we have revised in our lab as well. This Fletcher formula is limited to the normal stress on the cross-section plane of the beam. Okay. This is the formula. Fletcher stress is equal to mi over y. M is the applied bending moment. I is the second moment of area or moment of inertia, and y is the distance from the neutral axis to the extreme fiber. So as we move away from the neutral axis, over this flexural stresses will increase. Okay. Then similarly, the shear stress formula. The shear stress formula for beams and for the shafts apply to only cross-sectional and longitudinal planes. Okay? So this one is the shear formula which we have studied in our lab class as well. Shear stress is equal to torque, okay, over the polar moment of inertia, which is the resistance to the torsion. So these two are basically fixed. So the variable is this radius of the shaft. So shear stress will vary with this radius, just like the flexural stress will vary with the distance from the neutral axis. The important point to be noted here that these flexural stress for flexural formula and the shear formula, this one as well, flexural shear stress. This you will study in detail in your shear center chapter, Flexus shear stress. This is your shear stress. This is first moment of area, second moment of area. This is the width, and it is exactly basically opposite of the flexural stresses. It is flexure shear stress is maximum. Flexure shear stress is maximum at the neutral axis and minimum at the extreme fibers, opposite of the flexure stresses. The important point we want, which I want to make it here, is that your these flexure formulas, shear formula or flexure shear formula, they are applicable to specific planes. So when we are calculating it, basically by default we are applying the loads in that along that planes. Is this point clear? If you have any question, please let me know. Okay. If no question, then we are now coming to our main stuff, that is normal stresses and the shear stresses. Okay? The normal stresses and the shear stresses. Before we proceed to this one, there is one figure which I want to share with you for the understanding. Let me open that. It was open, then suddenly I closed it. Okay, we can have it later on. So let's consider this element. Okay, so how we are proceeding? This is your element. You have divided this element into finite number of units, and this is one unit. On this one unit, we want to work. And we want to calculate the normal stresses and the shear stress is acting on this element. ठीक है जी? In the figure you can also see this is the bending moment, fine, and this is the twist. You can see the twist is applied perpendicular to the longitudinal axis, and this bending moment is acting within the line within the plane. Okay, now this 3D unit we are going to study. So in general, this is triaxial stress state. What is triaxial stress state? You have y-axis, this is your y, this is your x-axis, and this is your z-axis. This is my z-axis, x-axis, and y-axis. ठीक है जी? I repeat, z-axis, x-axis, and y-axis. Triaxial stress. So now the point to be noted, let's say first I am just focusing on this plane which is towards the x-axis. Now we are just seeing this, that there is a stress which is acting along the x-axis. So this stress is your normal stress. ठीक है जी? Normal stress. ठीक है जी? Normal stress which will result in either tensile stress or compressive stress. So in this case, normal stress sigma xx is acting along the x-axis, and this stress will produce what you say elongation, because it is positive. It is trying to elongate the element. This is sigma x, and the complementary of this sigma x is this stress. ठीक है जी? Complementary means that it's the same stress but with opposite sign. ठीक है? Means it is acting in the opposite direction. Magnitude is the same. Fine. Then these are the two shear stresses. ठीक है जी? Now how we are going to designate these two shear stresses? So how we are going to do it? So this shear stress acting on the x face, so that will be tau x, and this is acting in the direction along the z-axis. So acting in the x-axis, and it's towards the z-axis. So this shear stress will be designated, so this shear stress will be designated as tau xz. ठीक है जी? Tau xz, this shear stress. It is in the x plane and it is acting towards the z direction. So first represents the plane in which the stress is acting, and the second subscript represents the direction in which this stress is acting. ठीक है जी? Then you have this shear stress. Now this shear stress tau x, because it is acting in the x plane, and it is oriented along the, or it is moving, or it is in the direction of the y-axis. So this shear stress is tau xy. Tau xy, oriented along the y-axis. ठीक है जी? So this shear stress is tau x. X represents the plane in which the stress is originated, and the y represents the direction in which the stress is applied. Tau xy and tau xz. So on this face you have one normal stress. ठीक है जी? One normal stress. Normal stress is represented by single subscript. You can even represent it with double subscript, but then it will be sigma x acting in the x plane along the x-axis. So it will be sigma xx. So normal stress is sigma xx or just sigma x acting on this face. Is this point clear? If not, I can repeat it. So let me repeat it for other dimensions. So now this is your z plane, this one, ठीक है जी? Because it is oriented in the z direction. Okay, so this normal stress sigma z, Z small first small subscript represents the plane in which the stress is acting, and the second subscript Z represents the direction in which the stress is acting. So sigma zz, this is the normal stress sigma zz, which is acting in the Z direction, normal stress. Now comes the shear stresses. Now if I see this shear stress, it is in the it is acting, originating in the plane z, and it is acting in the x direction. So in the book they are not following this what you say convention, but I will let you know why they are not following it. So according to over convention, this shear stress is tau zx, because it is originated in the z plane and it is oriented along the z direction. Sorry, oriented along the x direction. So it is tau zx. ठीक है जी. Now tau zx shear stress, it is complementary to this tau xz. So basically tau xz and tau zx, they are complementary stresses, means their magnitude will be the same. So in the book what they are saying this is tau xz and this is also tau xz, because they have the same magnitude. But according to over convention, it is tau zx, and it is complementary stress to this tau xz. Is this point clear? Clear?
Yes, sir.
If
Clear.
you okay, then you have this second shear stress that will be tau zy, originated in the z plane and oriented along the y direction. So tau zy. ठीक है जी. And why it is why they are saying this tau yz, because it is complementary to this. ठीक है जी. So this shear stress is complementary to this shear stress. So on this face there is one normal stress sigma zz, and there are two shear stresses tau zx and tau zy. Then comes to this y plane. ठीक है जी. और y face. Now on this y face you have this normal stress sigma yy, originated in the y plane and it is along the y axis. So it is sigma yy, normal stress. ठीक है जी. Now comes the shear stresses. So this shear stress will be tau yz, tau yz. ठीक है जी. Tau yz, so this is complementary to this tau zy. ठीक है जी. So tau yz is complementary to tau zy. Fine. Then you have the shear stress, this tau yx, tau y first should be y, second should be x, tau yx, and this shear stress will be complementary to this tau xy. Is this point clear? ठीक है. tau yx complementary to tau xy. Now comes to this point, the general state of the stress triaxial. Triaxial means three axes, x, y, and z. At a point is characterized by six independent normal and shear stress components. Means three normal and three shear stress. We can find them: sigma x, sigma y, and sigma z. These are your three normal stress components: sigma x, sigma y, and sigma z. These are your three normal stress components. ठीक है जी. Then comes the shear stress component. Tau xy, tau xy, and tau yx, they are complementary to one another, so it is considered one shear stress. Tau yz and tau zy, these two are considered complementary to one another, so tau yz will be considered one shear stress. Then you have this one, tau xz and tau zx. These two will be considered complementary to one another, so one stress will be considered. So now you have three normal stress components: sigma x, sigma y, and sigma z. And similarly, you have three different shear stress components. Find tau xy, tau xy, tau xz, and tau yz. ठीक है जी? So very simple to remember. Tau xy, tau xz, tau yz. ठीक है जी? So you have three different normal stresses and you have three shear stress components. ठीक है जी? So this general state of the stress at a point is characterized by three normal stress: sigma x, sigma y, and sigma z, and three shear stress components: tau xy, tau xz, and tau yz, which act on the faces of the element of the material located at the point. Now, another point which I want to discuss with you here, that this is three-dimensional element, so it has six faces. So it's a three-dimensional element, so it has six faces. So this is face X. So complementary face of this is this one. Okay? So that's why they have shown the this complementary normal stress of this. Then you have this face which is along the plane Y. The complementary of this is this one. Okay? The complementary of this is this one. Okay? And you can see this is normal stress Y and the complementary normal stress Y is shown. Then you have this face Z. Okay, the complementary normal stresses and shear stresses to this face Z will be these ones. Okay, and you can see this complementary normal stresses shown. So now just come to this point. There are six faces. Okay, on six faces, each face is complementary to one. Okay, so six faces are reduced to three faces. Okay, then on the three faces, you have at each face you have one normal stress and two shear stress. Now, these on three faces, these stresses are reduced to three normal stresses and three shear stresses. Okay, so if you can find three normal stresses and three shear stresses, okay, you can analyze whole of this unit, and which means you can analyze whole of this element. Is this point clear to you guys? Clear? Not clear. Guys, can you hear me?
Yes, sir.
If you have any question, you can ask me. User, any questions?
No, sir.
Gianni Pereira, any question?
No, sir.
Okay.